Hi everyone, and welcome to the new session of the Research Seminar Series hosted by Nomadic Labs. Today's speaker is Dario Fiore, an Associate Research Professor at the IMDEA Software Institute in Madrid. And in this talk, Dario will give an overview of the work on Succinct Zero-Knowledge Batch Proofs for Set Accumulators, where he will present new techniques to efficiently combine zero-knowledge snarks with RSA accumulators. Feel free to ask your questions directly in the chat, as we will have a Q&A at the end of the presentation. So I hope you like the event, and let's start.
So good afternoon, everyone, and thanks Nomadic Labs for inviting me to give this talk. So I'm Dario Fiore from IMDEA Software, and I'm going to talk about Succinct Zero-Knowledge Batch Proofs for Set Accumulators. And this is a joint work with Matteo Campanelli, Semin An, G.K. Kim, Dimitris Kolonellos, and Yuno. So let me start by describing what is the main problem that we address in this work, which is that of batch membership proofs. So the idea is that we have two users, a prover and a verifier, that have both access to a large set S. And the goal of the prover is to convince the verifier that he knows a subset of elements, xi1, xim, for which some property P holds. So notice here that we want to prove membership for a large set and for a batch of elements, plus some additional property. And we have two main desired properties that we would like to achieve. One is efficiency. Ideally, we would like to have the verifier, the communication to and the verification time to be polylogarithmic in the size of the set and the size of the batch, but even constant. And another property that we want to achieve is privacy, and in the sense that the verifier should learn no information about the batch of elements for which the proof is done. So what is a motivation for batch membership? One motivation comes from blockchain applications. Indeed, in a blockchain, besides being a chain of blocks in which we record transactions, it is also associated to it a global state. So at a certain point in time, there is a global state. And when a new transaction is broadcasted and should be validated, what typically happens is that validators run two types of checks. Some checks are local to the transaction. For example, you may check that the transaction is correctly signed. And some other checks are global in the sense that you want to check that the transaction is consistent with the global state. For example, like the transaction involves like a user that has enough money to spend, but for this you have to look among all the sets of active users. And if we look at specific blockchain projects, we have several examples of these global states. For example, in Bitcoin, we have the set of spend transaction outputs that are essentially the set of spendable coins that used to avoid double spending. In Zcash, there is the set of nodes that are all the coins that have been created so far, or the set of account balances in Ethereum, or in like slightly different or non-cryptocurrency related blockchains like decentralized identity systems. The global set would be the set of commitments to identities that are being created and claimed up to a certain point. And in all these examples, you have this fact that you run two types of checks. As an example, in Zcash, you are checking globally that a coin exists, so it's among the set of nodes that exist. And at the same time, you don't want to reveal which coin you are using, so for anonymity reasons. And also you want to prove additional properties about the coin, simplifying things a little bit. This coin is a commitment to some unique identifier and some value, and you want to check that, for example, the value is greater than the amount one wants to transfer. So, and a challenge that happens if we talk about blockchains is that these global states grow more and more with the time. And so we want to make verification scalable. So we want to scale to large sets, but also to large batches. And also we want to avoid, storing from the point of view of the verifier this global state. So it's a very intriguing question whether storing the global state is necessary for verification. So the second problem that we address is related to sets, and it's that of batch updates. So again, we have prover and verifier, and they have access to two sets, S and S prime. And S prime is a set that is obtained by from S by removing some elements, in this example x4 and x5, and by adding two more elements, y4 and y5. And in this context, the goal is that the prover wants to convince the verifier that there exist sets of elements xi's and yj's, so that S prime can be computed from S by removing the xi's and adding the yj's. And also for these elements that are involved in the update, some additional property holds. So again, there is a main desired property that we want to achieve here, which is efficiency of processing updates, in the sense that the communication and verification time should be, again, polylogarithmic the size of the set and the batch, or even constant, ideally. And notice that privacy is less of a concern in this case of updates, because like the sets are actually public, so you can always look at the differences of the two sets to understand which elements are being swapped. Okay, so and what's the motivation for batch updates? One motivation also comes from blockchains, and in particular, it's the problem of on-chain scalability. So, it is known that if we want to make blockchain scale to large number of transactions, there is a problem because there are only a few number of transactions that can fit into a block. So in order to solve this problem, there are several proposals that are being considered. One of them is the one based on so-called having a layer 2 for transactions. And among the ones that are based on layer 2, there is an interesting one that fits the case of batch updates that is called ZK rollup. So this idea is being proposed by Barry Whitehead in 2018 and roughly works as follows. So again, let's consider that at a certain point in time, a blockchain is associated with a global state. Let's call it S0. So the ZK rollup idea consists into introducing an aggregator node that would first collect a batch of transactions, M transactions. So, here M should be a large number, for example, maybe 1,000 transactions, 10,000 transactions. And then the aggregator would execute these transactions locally and would compute the state SM that is obtained after executing all these transactions. In fact, notice that executing each transaction would cause to go from a state S0 to a state S1, in which there has been some swapping of elements, and so on and so forth, until reaching the state obtained after applying the last transaction, the nth one. So after it computes the state, then the idea is that the aggregator would only post a proof about the existence of these M transactions and that of the appropriate swaps that have been involved with executing these transactions. In particular, it means that the aggregator would produce a new state and prove the correctness of its computation and validity of all the transactions that he collected. And so if he would send these proofs and the validators accept the proof, then the new block will only include this proof. Now, for this reason, we would like this proof to be as short as possible, and in particular to be shorter than the length of transactions. So again, here the challenge for scalability is that we would like to have the validators ideally work without storing the set and to have this proof as short as possible. And to, of course, scale it to large batch size. Okay, so that's the context in which our work operates. So let me now give you a very high-level view, so an airplane's view of our work, in which we develop succinct proof systems for these two problems. So zero-knowledge batch membership and batch updates, also known as multi-swaps. Again, our goal is to actually achieve communication and verification times that are constant in the size of the batch and the size of the set. And let me now say what is our approach. So first, in order to achieve this goal that the verifier's input can be constant size, we make use of cryptographic accumulators. So in a nutshell, these are cryptographic primitive that allows to represent succinctly a set. And then in order to achieve short proofs and short verification time, we will combine accumulators with ZK snarks. So now in this approach, there is nothing particularly new. It's actually a folklore approach to solve this problem, but our technical contribution and novelty is into proposing new techniques that allows to use together these two objects in an efficient way. And in particular, we will focus on RSA accumulators with ZK snarks. Okay, so here is the roadmap of this talk. So I will first explain a bit better this approach. And for this, I have to recall exactly what are accumulators, what are ZK snarks, and how we can use them together to do batch memberships and batch updates. I will discuss what are the limits of this generic approach if we want to instantiate it with state-of-the-art solutions, and this will motivate our new results. And I will explain them, and in order to do this, I will first have to recall what are RSA accumulators, commit and prove snarks, and a few more techniques. And finally, I will conclude by discussing the evaluation of our solution. All right, so let's first see what are cryptographic accumulators. So this is a cryptographic primitive proposed in 1994 by Benalo and Demare. And again, the idea is that there are two parties. We call them prover and verifier. That have access to a set. So, okay, first, like the accumulator has some setup algorithm that generates some public parameters. And then with these parameters, we can accumulate, so we can compress a large set into a short digest. We call it ACK. And that's what is going to be stored by the verifier. And then the prover wants to convince the verifier about some element X being in the set that is accumulated, can use a proof membership algorithm given the set and the element X, that in order to generate a so-called witness or a membership proof, WX, that would be verifiable by only knowing the element X and the accumulator ACK. And in terms of security, accumulators have this guarantee that it is computationally hard to generate valid membership proofs for elements that are not actually in the set. So, so that's the security property that they have. Okay, so in our work, we actually use an extended notion of accumulators that are dynamic accumulators with batch proofs. That is based on extensions proposed by Kamenisch and Lisiaskaya and Bonnet, Bunz, and Fish in 2019. So what is the difference with the standard notion of accumulators? It's what is in red in my slides. So first, proofs are about batches of elements. So it's not a membership proof for a single element, but for m elements simultaneously. And the other detail is that we actually work with multi-sets. So S is a multi-set, not just a set. So in the sense that an element can appear more than once. And the other property that is related to the fact that these are dynamic is that there is an efficient insertion algorithm that, given an accumulator and another set X prime, it can compute an accumulator to the set S union X prime. So if S was the set in ACK, then ACK prime is an accumulator to S union X prime. And notice that this can be done efficiently in the sense that you can do it by only knowing the new sets and not necessarily knowing the originally accumulated set. All right, so this is the notion we want to work with, and one question one may ask is whether we're done. So if this solves our main problem, and unfortunately not. In fact, the first problem is that the verifier in this solution, as you can see, has to read the set X. So the batch of elements, he needs to read it because he is verifying membership for it. So this means that the verification time must be at least linear in the size of the batch. And the second problem is that accumulators are only about membership proofs, but not about proving additional properties of the elements for which we prove membership of. So to address the latter question, we are now introducing the use of ZK-SNARKs. So these are zero-knowledge, succinct non-interactive arguments of knowledge. It is essentially they are a proof system that enable a party called prover to convince another party that is the verifier about the truth of an NP statement R. So in particular, the prover wants to convince the verifier that R of XW accepts. And for this, it will use this proof system that consists of a setup algorithm that, given the description of a relation, outputs a common reference string. And then the prover algorithm, given the statement and the witness, can produce this non-interactive proof that can be checked by the verifier. So in particular, if the prover is honest, the verifier will accept. And then the ZK-SNARKs are secure in the sense of being knowledge sound, which means that a computationally bounded prover must know a valid W. And then an interesting property is that these proof systems are supposed to be succinct in the sense that proofs are short and easy to verify. So more precisely, proofs are required to be polylogarithmic in the size of the relation or even constant. And also verification time in a similar way is linear in the size of the statement X and polylogarithmic in the size of the relation. And again, this can be also made just linear in the size of the statement for some constructions. So the final property that is interesting about ZK-SNARKs is zero knowledge, which informally says that proofs completely hide the witness W, beyond what can be trivially implied by the fact that a relation for X solves. Okay, so this is these are ZK-SNARKs. It is a informal definition, but it should be fine for the sake of our talk. Okay, so now that we know what are accumulators and ZK-SNARKs, let me describe what is this solution that can combine these two objects in order to do batch memberships, and in particular proofs that can prove membership and some additional property. So it's essentially a folklore idea, and the idea is to use a ZK-SNARK for the following composed relation. So this is an NP relation that takes as a public statement the accumulator ACK, and as a witness a set X, an accumulator membership proof WX, and some additional witness W. And this relation is true if and only if the WX is a valid membership proof for the set X and accumulator ACK. So the verification algorithm of the accumulator outputs 1, and this additional property on X and W is also satisfied. So this means that by considering this relation, we can use a ZK-SNARK that supports this relation in order to convince the verifier that X is a subset of the accumulated set for which the verifier has the accumulator, and this additional property P on XW holds. And notice that by the accumulator security, the fact that the accumulator verification is satisfied means that actually X is part of the set. And in a similar way, we can use ZK snarks and accumulators to prove batch insertions, which is a problem similar to that of batch updates, in which we only prove that there has been some new elements added to a set S. So more precisely, assume that the prover wants to convince the verifier that S prime is S union Y for some Y for which a property P holds. Again, we can use a ZK-SNARK for such a relation that instead of proving the set union, we would use the insertion algorithm of the accumulator. So in particular, given two accumulators, ACK and ACK prime, and as witnesses a set Y and some additional element W, we can prove that ACK prime is obtained by doing insertion on ACK with set Y, and P of YW is 1. And again, by the correctness of the accumulator, this implies that if ACK is an accumulator to the set S, then ACK prime will be an accumulator to a set S union Y. All right, so this sets the context in which we want to work on. Oh, and by the way, right, so we have moved to batch insertions, but in my previous slides, I was talking about batch updates, so which are also called multi-swaps. So the fact that we also remove elements, not only insert ones. However, an observation that was recently done in a work by Özdemir et al. Is that having insertion is sufficient to also do multi-swaps, and that is that if you have a multi-swap, so we remove some elements X and we add elements Y to S to reach a set S prime, then it actually means that there exists an intermediate set S mid in which that is obtained by inserting the set Y into S, and such that S prime is obtained by removing X from S mid. But it's even more. So using the fact that removal and insertion are dual, we can also think of S mid to be the outcome of inserting X into S prime. And with this observation, it means that we can express a multi-swap relation over two accumulators, ACK and ACK prime, with the end of two insertion relations that involve ACK and ACK prime, in particular by showing that there exists an accumulator to this intermediate set, so that this intermediate set is obtained by inserting Y into ACK and is also obtained by inserting X into ACK prime. So, because of this, from now on, we will mostly be concerned with constructing proof system for batch insertions, and using this trick, they will imply proof system for multi-swaps. Okay, so now that I've introduced what is the setup and what is the main approach, I want to discuss what's the state of the art in instantiating this approach. So let's consider first the problem of proving batch membership in zero knowledge for a set X, for a set S of size n, and a batch of elements X whose size is n. So there are two main constructions of accumulators that we are going to consider. One is a very popular one that are Merkle trees. It's based on collision resistant hash functions. And another one is that of RSA accumulators. Let's first compare these two constructions in terms of, just as accumulators. So the first parameter we're going to consider is what's the size of the proofs. So it turns out that Merkle trees actually do not really support batch membership proofs. In fact, a batch membership proof for M elements is just a concatenation of M proofs, one for each element of the batch. And this means that the size of the proof would be O of M log n. Whereas RSA accumulators have this nice feature that they have succinct batch membership proof. So it's just one single group element. So they're constant. In terms of verification time, things we have to consider the fact that the verifier has to read at least the batch of elements X. So in this sense, RSA accumulators are optimal in verification time. For Merkle trees, they have an additional log n factor, which may not be too bad, however, in terms of verification time. So things are instead much more complex when it comes to using these two accumulators in this approach in which we want to use a Zk-SNARK that proves that their verification is correct. And here the problem is that we have to encode the verification algorithm of the accumulator in the constraint system of a Zk-SNARK. And unfortunately, these things are not very efficient in this sense. And for Merkle trees, the main problem is that we have to encode roughly O of m log n hash operations into the constraint system. And this can be concretely costly, even if we use a very cheap hash function for SNARKs like Poseidon. Then for large batches or for large M, this is a significant cost. And this is even worse if we use more standard hash functions like SHA-256. And in the case of RSA accumulators, the problem is to encode RSA group operations into Zk-SNARK. So these are also very costly. So we can estimate them with roughly 1.8 million constraints per element of the batch. So this suggests that there is not really a scalable solution for proving batch membership in zero knowledge. In the context of batch updates, things are quite similar for Merkle trees, as in fact a Merkle tree-based solution for updates is almost the same as proving membership. And in the case of using RSA accumulators, there is a recent work by Özdemir et al. That shows new techniques for using Zk-SNARKs with RSA accumulators efficiently. And however, their technique does not support zero knowledge. That's why it does not work in the case of batch membership. But nevertheless, for the case of updates, they show they can surpass Merkle trees, but for quite large batch size. But I'll discuss more of this later when I will mention the evaluation of our solution. Okay, now, given the state of the art, I can give you a more precise view, a bird's eye view on our work. Technically, we propose new techniques to use together Zk-SNARK with RSA accumulators efficiently. And our first result is a commit-and-prove Zk-SNARK for batch membership. We call it ARISA, so it's an elements hiding argument for RSA accumulators. And at the core of ARISA is a new randomization technique for RSA accumulators witnesses, and also a new way to encode RSA accumulators verification in SNARKs, but out of the circuit. So that's why we can achieve scalability. And then we also propose a companion proof system called BINS-ARISA, which is a commit and prove SNARK for batch insertion. And that, as we discussed earlier, it also implies multi-swaps. So, and finally, we also do an implementation and evaluation of our proof systems. And, I'll discuss the highlights of this evaluation at the end of my talk. But in a nutshell, we show that we can improve over solutions based on Merkle trees. And for the case of updates, we also show improvements in the case of multi-swaps compared to this recent work by Özdemir et al. Okay, so what's the rest of the talk? So I will give an overview of our solution. So now I'll be more technical. And to this end, I will have to first recall what are RSA accumulators, commit and prove SNARKs, and then I can describe what our protocol is. Okay, so let's begin with RSA accumulators. So the setup algorithm of these accumulators consists into generating a group G of unknown order and some generator little g of this group. So this group can be instantiated, for example, with a classical RSA group, Zn star, where n is the product of two prime numbers. Or we can also instantiate it with class groups, which have the advantage of allowing for a transparent setup. So another observation is that for RSA accumulators, we have to consider sets of prime numbers. And I'll discuss later how we can actually get rid of this limitation. So the accumulation algorithm, so in order to compress this set, we will exponentiate the group element G by the product of all the elements of the set. So, x1 times x2 times xn. So this is the accumulator that is then given to the verifier. And then when we want to prove that a certain batch of elements U1, U2, UM is part of the set S, the prover will generate a group element WU, which is obtained by raising G to the power of all the Xi's in the set divided by all the UJs that are in this batch. And notice that if these UJs are really part of the set, this exponent is going to be an integer, so the prover can generate this, this group element. And if not, this exponent is not going to be an integer, and under the strong RSA assumption, it is computationally hard to generate such an element. So this group element W is given to the verifier that can simply check that this batch of elements U1, UM is part of the set by doing one exponentiation. So, and in terms of insertion, it is also a very simple algorithm. So if we have this accumulator ACK and we want to add to the set elements Y1, Y2, YM, we just raise ACK to the product of these elements. And that's our ACK prime. Okay, so that's our first object. Our second object that we use for our protocol are commit and prove ZK-SNARKs, also called CP-SNARKs for short. So these are essentially an extension of ZK-SNARKs that allow to make proofs about data that the verifier cannot see, but so that you can make a reference to this data. So in particular, more precisely, this means that both prover and verifier have access to a commitment CU, and this is a commitment to some data U, and the proof is about UW being in the relation R. So what the prover is convincing the verifier about is that he knows some W such that R of UW accepts for some U that is inside the commitment. So more formally, these are ZK-SNARKs about the following RCOM relation that takes as public input a commitment CU, and as a witness this data U, an opening of the commitment, and some additional witness W, and he proves that R of UW accepts, and that C is actually a commitment to U. Okay, what is really useful about commit and prove SNARKs? And in particular useful for our work. So it's a property that was highlighted by in a work by Campanelli, myself, and Anaïs Carroll in 2019. That is about showing that you can use commit and prove SNARKs to efficiently create modular proofs. So assume that you have now, the idea is the following. So assume that you have two commit and prove SNARKs, CP0 and CP1, about respectively relation R0 and R1. And that you want to prove that at the end of these two relations on a joint input U. So that R0 of U, W0 holds, and also R1 of U and W1 holds. So this can be done very simply by generating a commitment to this joint state U. And notice that this is a succinct commitment, supposed to be a succinct commitment. And then you generate a proof by 0 using the first CP-SNARK and the proof pi 1 using the second CP-SNARK. And importantly, these proofs must be about the same commitment CU. So if both proofs refer to the same commitment, then we can obtain that these, the concatenation of these two proofs imply a proof for the end of the two relations. Okay, so these are the two main building blocks of our protocol. Let me first state what is exactly ARISA, what does it do? So it's a CP-SNARK for batch membership in the sense that it can, it's a ZK-SNARK for the following relation, membership relation. So it's a relation that takes as public inputs an RSA accumulator ACK and a commitment CU, and this is a commitment that we will instantiate with the Pedersen commitment to a vector of integers over a prime order group. And then the witness is a vector of integers, an RSA accumulator witness WU, and an opening of this commitment. And what the relation says is that W is a valid membership proof for the elements in this vector, and that these elements are in the commitment. So why are we designing ARISA to be commitment proof? And the idea is that by doing so, we have a very modular gadget that can be used to prove any other property R about the elements for which we do a membership proof. And this can be done by simply using this composition idea that I described in the previous slide, and by composing ARISA with other commitment proof, for example, about another relation R. So, and by doing so, we obtain another commitment proof argument that can prove membership in S and additional properties R. And interestingly, as a byproduct of this, we can also compose ARISA with the commitment proof argument that can prove hashing relations, in particular hashing to prime relations, in order to move from working with sets of prime numbers to working with sets of arbitrary elements. Okay, so now let me describe how the protocol works. So our starting point is a sigma protocol for the accumulator verification equation. So let's recall the setting. The verifier as an accumulator ACK, the prover as a element WU, such that this relation also W to the product of the UIs is ACK, and they both have access to a commitment CU. And the prover wants to convince that the verifier that this relation holds for the same UIs that are committed. So as a first call, let's see how we can hide the exponent. So let's notice that this verification equation is an exponentiation. And for this, the first idea is to use a classical Schnorr protocol to hide the exponent of this exponentiation relation. So this means that the prover can sample a sufficiently large integer R, send to the verifier W and W to the R, then the verifier would sample a random challenge H, and the prover would reply with R plus H times the exponent, which is the product of the UIs. And this is the verification equation for the verifier. So the good news of this is that it actually convinces the verifier that the prover knows the exponent of this accumulator's verification, but there are still some problems and challenges to be overcome to achieve our our goal. The first one is that in spite of using a sigma protocol that gives us zero knowledge, we are not really hiding the exponent. And the problem is that in order for the verifier to check this proof, the verifier should know the group element W, which means that he can test the verification for example, if he tells a candidate batch of elements. So essentially, we are not really achieving zero knowledge. The second problem is that it is clear that this sigma protocol is completely detached from the commitment CU. So we are not proving that any linking with the commitment. And third, this sigma protocol is not succinct because the size of the third message, the integer k, is an integer of m bits. So is roughly as long as the size of the batch of elements. So, the next part, in the next slides, I'm going to show you how we can solve each of these challenges and finally achieve our main goal. So the first idea is a technique to randomize RSA accumulator witnesses. So let me first describe it alone in this slide, and then we'll see how to use it in the sigma protocol. So assume that we have an accumulator to a set of elements x1 and xn, and a witness for a batch of elements UIs. So the first thing we will do is to select a set of very small primes. So let's think that they are the first 2 lambda prime numbers, 2, 3, 5, 7, up to the 12th one. And what is important here is that we have to ensure that these sets of elements is disjoint from the set of elements of which we want to prove membership of. So, and this can be guaranteed if we, for example, all the xi's in the sets are larger than the largest of these small primes and P2 lambda. So the first thing we will do is to transform the accumulator to S into an accumulator to that set union these small primes. So we are essentially using the insertion algorithm to add these small primes to the set. And we will now work with ACK@. And the second thing we are going to do, which is actually the main technique, is to add a random subset of the small primes to the witness. So more precisely, we are going to sample two lambda bits, B1, B2 lambda in 0, 1. And so that, with the probability 1/2, we are going to include each prime include each prime in the set. So more precisely, we are going to compute these two integers S and S bar, and we are going to raise W to S bar. So intuitively, what is happening is that now the resulting WUF is a membership proof for not only for U1, UN, but also for all the PI, so the small primes for which the bit is 1. And of course, now for the new accumulator ACK@. And you can see here the verification equation why this holds. And it's based on the fact that S and S bar, the product of them reaches the product of the small primes. So now why this new witness is hiding? So the idea is that this new witness is raised to a random number S bar, and based on a suitable assumption that we call DDH2, the resulting element is computationally indistinguishable from random in over the hidden order group. So this is a technical property, and for this to hold, we use the fact that S is a random integer over a range of 2 to the 2 lambda values, such that all the values that we can reach are distinct, as S is a product of prime numbers. So I'll refer you to the paper for a more technical explanation of why this is hiding. So then we will use this technique in our Sigma protocol, and since we are modifying the Sigma protocol I showed you before with the new parts are in red. So what happens is that we select these small primes that are common to prover and verifier. Both prover and verifier go from ACK to ACK@, so to the new accumulator. And then the prover randomizes his witness in this way, as I described before, and then runs a Sigma protocol for the randomized witness. Notice that now the Sigma protocol is about proving not only membership of the UIs, but also of the selected small primes. So this integer S. Okay, so what are the problems with this solution? So first of all, we achieved our goal, so that now this Sigma protocol is zero knowledge. So in the sense that we are hiding actually the elements of the sets for which the accumulator's verification holds. But still there is no link with the commitment, and it's not succinct. So in order to establish a link with the commitment, what we do is to link the Sigma protocol to the commitment through the response. So the idea is that the response K of the Sigma protocol is about some elements UIs. So what we will do is to use a commit and prove SNAR for an arithmetic relation that is going to prove that K, this integer, is well formed. In particular, it is really R plus HS UIs for the same UIs that are in the commitment. So, and for this, this is a more technical point. We have to add a commitment to the integers R and S. So we have this proof about the arithmetic relation. So this proof actually provides a link between the verification of the Sigma protocol and the commitment CU, which solves our second challenge. But still we have the problem that this protocol is not succinct because K is long. Now, in order to to solve this last challenge, we are introducing the use of a PO-key protocol. So this is a proof of knowledge of exponent for hidden order group. It's a protocol proposed by Bonnet, Booth, and Fish, which is essentially an argument of knowledge for this exponentiation relation that is succinct with respect to the size of the exponent y. So y can be essentially an arbitrary long integer, but in this protocol, the verifier would only get y model, where L is a random prime chosen by the verifier of essentially 256 bits. So that's why the protocol is succinct. So this means that for our protocol, we are going to let the prover generate a PO-key proof for the this verification equation of the Sigma protocol. So it's about proving knowledge of K, so that this holds. And for this reason, we can replace this verification with a PO-key verification. And also, we don't have to send the integer K. So the good news is that this makes our proof succinct, but the bad news is that we lost the link to the commitment again, because the arithmetic proof was about linking with the integer K, and now we're no longer sending K. So to solve this last problem, what we do is to observe that actually inside the PO-key proofs, it comes the integer K model. So what was supposed to be K, now actually the prover sends K model, where L is a small prime. So what we actually do is to have the arithmetic proof to also to prove that K prime is correctly computed. And one thing that I haven't mentioned is that the arithmetic proof also has to ensure that all the UIs that are committed are greater than P2 lambda. And that's essentially to avoid that there could be common elements among the small primes and the elements of the batch for which we do a proof. All right, so this is eventually our last protocol. We can see now we can achieve a full link from the commitment to the proof, and we have succinctness. So, okay, so I want to mention briefly how we handle batch insertions. So the idea is very similar, because actually an insertion proof is the same type of relation as a membership proof when it comes to ERC accumulators. And in fact, our protocol is a simplified version of ARISA, in which, since we don't have to achieve zero knowledge, we don't have a Sigma protocol. So we actually just use a PO-key proof, and we pair it with an arithmetic relation proof with using a commit and proof snark. And but there is a technicality when handling insertions, which is that we can no longer trust the fact that the elements the prover is inserting are prime numbers. Whereas in the case of batch membership, there we are assuming that the set is being constructed honestly, because, for example, the consensus rules in a blockchain are making sure that you add appropriate elements to the accumulator. So our solution to deal with this problem is to use a division intractable hash function. So this is a hash function that, roughly speaking, is such that it outputs integers on input some elements x size, so that with very high probability or with overwhelming probability, these integers contain a unique large prime. The bad news is that the output size of this division intractable hash, in order to guarantee this security property, have to be of roughly 2000 bits. Even if the hash, they can be instantiated by doing the addition of a let's say, standard random oracle hash function with a constant of 2000 bits. So, but this requires another additional proof to check that the the elements of the sets are actually being hashed correctly. Okay, so I'm going to use the last minutes of my time in order to discuss an implementation and instantiation of our proof systems. So in particular, we instantiate our commit and proof building blocks with the Lego Groth16 commit and proof snark, which is a variant of Groth16 that is efficiently commit and proof, proposing the Lego snark paper. And we do an implementation over the BLS 12381 leap curve. And we use RSA accumulators of an RSA group with the 2048 bits modulus. And for hash functions, we use Poseidon and SHA-256 in different benchmarks. So we implemented this on C++ based on the on libsnark, and we use xjsnark as to generate some R1CS gadgets for integer arithmetic. So for our evaluation, we for batch membership, we compare ARISA versus Merkle tree-based solutions with different hash functions. And for updates for multi-swaps, we compare Beans ARISA with a solution based on Merkle trees and the recent work of Ozdemir et al. Okay, so about batch membership, we can see that ARISA has pretty good proving time. So our benchmark mainly focused on proving time, which was the main bottleneck in state of the art. And we can see that, for example, if we consider Merkle trees of depth 32, ARISA can have between 10 and 30 times faster proofs. And actually, the improvement becomes even larger for larger batches. So here in our benchmark, we consider batches between 1 and 64. And if we consider Merkle trees with more complex or more expensive hash functions like SHA-256, then the difference can become even much more. In ARISA, we actually pay a little bit in verification time and proof size, which is roughly double and 4 times that of a Groth16 proof. But still, these numbers are quite practical. We also benchmarked the system in a decentralized ID application, in which essentially we, in order to, in addition to prove membership, we also prove some additional property, like proving some range checks on, for example, ages, just to test what's the relative cost of improving membership in a more concrete application scenario. And even in this case, we observe improvements, for example, compared to the SHA-256 based solution. And notice that even the ARISA DID construction was using SHA-256 in order to commit to identities. And another benefit of ARISA is also that by using much smaller constraints, we also have a smaller CRS. For example, even for a batch of size 1, it is 5 times smaller, which entails much less RAM consumption during proof generation. So in the case of multi-swaps, we did not run a full the full implementation, but we rather used a cost model based on number of constraints, and we consider sets of size 2 to the 20 for this, and we compared a solution based on Merkle trees, one based on the recent work by Ozdemir et al, and our based on Beans ARISA. And we can see that our Beans ARISA scheme has a competitive prover cost that can improve over Merkle trees and over these work by Ozdemir et al already for 1,000 sites-based number of swaps. And in particular, the break-even point compared to Merkle swaps is at roughly 140 swaps, whereas the previous work was breaking even at 1,400 swaps. So some comments on BINSA result, like, to conclude. So this is still quite expensive, and in particular, the most significant overhead in doing the multi-swap proof is the computation of ACK prime, and this is due to the fact that we have to perform deletions in RS accumulators that require essentially to go over the entire set. And also the fact that we are using a division intractable hash, and so large integers make it slower too. But on the good side, if we compare to Merkle swap, this type of computation is quite parallelizable and less memory intensive compared to, doing generating a proof with a gigantic constraint system of, for example, 180 million constraints. Okay, so to summarize, the main motivation of our work was that there was no scalable solution for proving succinctly batch membership in zero knowledge. We addressed this problem via new techniques for using together RS accumulators and ZK snaps. And we also apply our techniques to multi-swaps of accumulated sets. So we run an evaluation that I've just discussed, and I'd be happy to take questions during the question and answer session, and thank you all for the attention.
Okay, thank you so much, Dario, for the presentation. And let's have a look at our questions in the chat.
Yes, thanks everyone for the attention.
So we still have no questions. I encourage you guys to write now, and maybe we can ask one question myself. So I wanted to know, Dario, you mentioned the fact that your scheme requires an RSA modulus with a known factorization. So I'd like to ask you how you are planning to generate this, and how costly would it be with respect to other trusted setup ceremonies, for example, Growth 16.1.
Yeah. So yes, right. So our protocol requires. Our protocol requires an unknown order group to be generated. And our implementation of the protocol used an RSA group, like a classical RSA group where n is equals to the product of two primes. And so this group can either be generated using some trusted setup. So it should be a dedicated trusted setup using some multi-party computation. That's an option. So there are other options is to use some existing RSA moduli that are supposed to be hard to factor. I think there are some of these that exist. But I also want to remark that the description of our protocols is quite generic and works with any order group, which means that they can also be instantiated with class groups. Nothing in our protocol prevents from using an instantiation with class groups, which means that you can generate the group in a transparent way. Okay. Yeah, I see that there is a question about it.
Yeah. So it's quite interesting. I had not thought about the fact that you could use one of those big RSA challenges, for example.
Right. I can see that Mark is asking how this would.
Yeah. So Mark is asking, do you have an idea of how this would? Well, okay, it's related to the same question. How this would port to class group?
Yeah. So the answer is that the protocol would remain unchanged because it's completely generic, and you just need to instantiate differently a building block. What I cannot say on the spot is how the efficiency is going to change, but essentially this is related to the efficiency of class groups versus RSA groups.
Okay. So while we wait for more questions, I also wanted to ask you whether you can parallelize the prover, given that it's usually the main bottleneck.
Okay, so right, part of the prover can be parallelized. in the sense that okay, we have to let's see in which protocol we are speaking about. So if we speak about the membership protocol, you can parallelize the prover consists into making the proof of the sigma protocol and then the proof of the snark. Now, if the snark is parallelizable, you can parallelize it. And for the sigma protocol, the operations are relatively cheap, so I'm not sure that there is a big motivation in parallelizing. But it's true that some of the operations are multi-exponentiations that could be parallelized. And an interesting thing is either in the protocol for batch insertion or for multi-swaps, because the prover has, actually I mentioned this in one of my last comments, the prover has to come up with an accumulator of the final set in which some elements have been removed. Now, the problem is that there is no efficient way to remove elements from RSA accumulators, right? And so this means that it has to recompute this accumulator from scratch it has to go over the entire set. So this is probably the most costly part of the prover of the multi-swap protocol. But the good news is that this computation can be parallelized because it's a very large exponentiation. That's what is actually the cost of generating this accumulator. And so, it's much more parallelizable than, for example, doing, parallelizing a snark prover.
Okay, yeah, thanks. So Mark is asking, he's saying, if I understood well, you use Pedersen hash on the RSA group. Does this impact the size of the RSA modulus? Is it 2048 bits enough?
No, we don't use Pedersen hash over RSA group. Actually, what I mentioned to be in the slides, the Pedersen commitment to the inputs, it's actually in a prime order group. So it's actually one of the main technical contribution of our work, which is to bridge commitment to the elements in a prime order group. So it's a vector of integers committed in prime order group with an ERC accumulator that is in an hidden order group.
Actually, I had a question about that myself during talk. Because you do that, then your elements, the size of your element is bounded by the prime order group, or not really?
No, not really. We show a generic way, to commit to integers in prime order group by doing essentially splitting of the integers. If your integer is larger than the prime order group, you would simply commit, you would take the bit representation and split it in two so that it fits the size of the prime order group. And then inside the proof, you would reconstruct this.
But you could have collisions, right? Between two integers that are congruent modulo p.
No, because you don't do modular reduction. So you essentially take your integer and you reduce it in base p. So if p is the prime order group order, you take the base p representation of that integer, and then you have to prove it that this is the case. So.
Okay.
But for example, if you have, your prime order group is of order roughly 256 bits, and you have an integer that maybe is 260 for some reason, it would just fit into 2. It would double.
Okay. Maybe I also wanted to ask, there is this part of the talk where you talk about making the last message of the Schnorr Sigma protocol succinct, with this idea of reducing it modulo prime that you call L. So this reminds me a lot of a trick used for time locks that has actually been used at Nomadic Labs in the time lock implementation. So it's something related to the adaptive root assumption. So does this ring a bell? And is it related to?
Well, it's related to the adaptive root assumption. In fact, our soundness proof for that part of the protocol reduces to the adaptive root assumption. And the technique comes from this proof. I mean, it really goes back to the Vesolowski's proof of exponentiation proof. I'm not familiar with the time lock patterns, but I guess that they used a similar technique. And one difference here is that the prover proves knowledge of the exponent without having the verifier knowing the exponent.
Yeah, I think it's a great trick, because maybe it's not very explicit from the slide, but if you don't reduce the modulus, I mean, you mentioned that number is huge, right?
Right. The number will be linear in the number of elements for which you are making the proof.
And you cannot reduce the modulus because you don't know the order of the group. So that's a very nice trick. So I don't know if there are more questions. Could keep asking. So, yeah, so what do you think? I mean, of course, you believe the work is very relevant and could be better than other approaches, like based on Merkle tree accumulators. But I would like to know your opinion on that. What are the advantages of using Merkle trees with respect to this, if any?
I mean, one advantage of using Merkle trees is probably that you can instantiate it just based on hash functions. So I think this is an advantage. And yeah, I don't know. I think like RS accumulators are seem quite competitive. I mean, for what we show, they can surpass Merkle trees in these applications, even though in some cases they are still expensive.
So we'll have to consider it at Nomadic, because the moment we're investigating the other direction. But very, very nice idea. So thank you so much, Dario, again. I don't know if there are more questions, but I guess we could also conclude here.
Yeah.
So if you want to add anything?
No, I mean, if anyone has more questions, you can reach me at my contacts by email.
Thanks a lot.
Yeah.
So thank you again, Dario, and thanks to the audience for attending this research seminar session, and goodbye. Oh, we have one last question by Puya Fashin. Puya says, somewhat low-level technical question. Okay. You mentioned somewhere you use the DDH2 assumption. I'm just curious when this comes up, and if you used fixed or randomized generator, and what the distribution for DDH2 is.
Yeah, okay, good question. So we use this to prove that this randomization technique provides hiding. And so why this? Because, yeah, maybe it would be used. If I could share my slide, it would be much easier. But I don't know how to do it. Let me see. Give me a second. Okay, let me try to share my screen. Do you see my screen?
I don't.
Oh, you don't?
Okay, yeah, something changed. Yeah,
okay.
You can see this loop.
Right, yeah. So, right, so let's even see it even in this slide. So we are sending this element WU to the S bar, but also WU to the R. Now, R is actually fully random. It's supposed to be a very large integer that essentially makes this element statistically close to random. But S bar is this product of small integers. So the size of this integer is not going to be, let's say, close to the order of the group. So we are using this DDH assumption to argue that this element is going to be computationally indistinguishable from random. And so that's what the DDH assumption, this DDH2 assumption says. In some sense, it's like a DDH2 assumption for small exponents. And technically, this assumption, it's okay. You should probably see at the paper, look at the paper to see the exact definition, but it's more like a DDH assumption when one of the two exponents is comes from some specific distribution, and which is not a uniform distribution. And in our case, the distribution is the distribution that generates this integer s bar. And it turns out that if this distribution is so-called well spread, so it's sort of well spread over the range, then this DDH2 assumption holds in the generic group model in this hidden order group. Yeah, so actually, like, our technique is mostly adapting an existing generic group proof that was done for DDH2 in prime order groups. We adapted to hidden order groups, and then we show that this distribution is well spread because the number of integers that you can reach essentially is the same as the number of bits that you can choose. So there are exactly 2 to the 2 lambda integers that you can reach because is a product of primes. Yeah, I hope it answers the questions.
Okay.
Yeah, the distribution is efficiently sampleable because you can see that you have to do a product of prime numbers, and these exponents are bits.
Okay, so Mac is asking another question. He says, if the elements of the sets are not guessable, do we still need hiding? In that case, how does this impact the protocol? He's thinking about using this for the Zcash protocol, for example, in which the elements of the set are already randomized commitments.
Yeah, it's a good question, but it's the problem is that the sets are public. So even in Zcash, the set of coins is public. So maybe I should stop sharing because maybe you see my...
Oh, I think you stopped sharing already.
Okay. So even if the set is public, so even if the elements of the set each are random elements, because, for example, they are commitments, I mean, more or less they are random. Then, if you have, for example, let's say that you are doing this proof and you have a candidate coin you want to test, you can still test, right, if you don't apply this hiding technique. So it's true that it's maybe 1 out of a million coins or more, but if you have one in mind that you want to test, if the proof is about that one, you could test it.
Okay. So if there are no questions, let's thank Dario again and everybody for coming, and see you next time.
Yeah. Thanks everyone for the attention and for joining.